Hello everyone, welcome to a new video. Here in this video we are going to discuss about a Reimannian exact penalty method. In the Reimannian exact penalty method, suppose we are having a objective problem as f of x such that h of x is less than or equal to 0. This is a constant optimization problem. First, so we will convert this constant optimization problem into an unconstant optimization problem. Step 1. So minimization of f of x plus we will consider the constraint in the objective function itself using a row parameter and then writing max of 0 comma h of x. So this is the constraint optimization problem. We have converted that into an unconstrained optimization problem. So I will justify how the max thing comes. Suppose now h of x can be less than 0 or h of x can be greater than 0, right? So when h of x is less than 0, then the max of 0 comma h of x will be 0 only, so the constraint is satisfied, no need of this term. When h of x is greater than 0, then this term will come as a row of h of x. So our unconstrained problem will be f of x plus row of f of x. So fair enough, whenever the constraint is not satisfied, that is h of x is greater than 0, our objective term becomes this with some value of the row. Now the problem is, so we can write with the max operator, but the problem is whenever we are trying to find the gradient of such kind of thing, having a max function in that, though the solution will get stuck in some kind of corner point, right? Because this is the max operator, so the max operator in the graphically, I will write it here. So graphically max operator is this. So at 0, whenever the point is at 0, whenever h of x is less than 0 is fine, whenever h of x is greater than 0 is fine, but whenever h of x is at any corner point, so here the gradient doesn't exist. So we need to convert this max operator into some smooth differentiable function. So that we learned in the earlier video, that we can convert a max operator, max of 0 comma h in our case, into the LHC term that we studied earlier. So u log of e to the power 0 by h plus e to the power h by u, this is the LHC part. So we converted max of 0 comma h into u log of e to the power 0 by u is a1 plus e to the power h by u. So we successfully converted max 0 comma h into u log of 1 plus e h by u. Now let's check the two condition. Whenever h is less than equal to 0, then this term will reduce to u log of 1, that is 0 only. Whenever h is greater than 0, this term will reduce to u log of e h by u, that is h. So fair enough. So max of 0 comma h can be written as LHC of 0 comma h. So we got the value. So now let's after replacing this with this term, so our max term is replaced by this term, right? Now we were worried that at 0 the gradient doesn't exist. So let's find the gradient of this term now. If we find the gradient of this term, so we got it as e to the power h by u by 1 plus e to the power h by u into gradient of hx. So now we can see that the gradient exists, right? The gradient exists, and this is a sigmoid function into gradient of hx. Now hx is any constant, hx is any linear constant, so that can be differentiable, and also this is a sigmoid function now. So this is I wrote it as sigma of h by u, and this is a smooth function. So I have written it in graphically. So graphically we can see that instead of the non-differentiable max operator, this is the graph of max of x comma minus x. So instead of max of non-differentiable, non-smooth max of x comma x, we converted into a very smoothly differentiable sigmoid function. So now the objective becomes f plus u log of 1 plus e h by u, and we have also shown the gradient of this part gradient of f part to f dash only we have shown. Now so the objective becomes this part, and we need to optimize this objective right now. So now you may ask that what are the rho values and what is the u value, because rho and u are the parameters. So the rho value keeps on increasing because we are trying to find the maximum of which this was our original function, no, mean of f of x, h of x is less than or equal to 0. So rho is enforcing the constraint, so rho value we will keep on increasing to a certain value. And what about the u value? As u value we have to decrease now. Whenever we will decrease the u value, then only this exponential part will increase. So finally we will increase the rho value in our steps of the algorithm, that is rho I plus 1 will be theta p of rho of I, where theta is greater than 1. So that means we are increasing the rho value subsequently in the algorithm steps, and we will decrease the u value eventually. So u decreases the every iterations. So this is how we update the rho and u value, and this is how we convert the function constraint optimization function f of x such that x of x less than or equal to 0 into an unconstrained optimization functions, and that too the max operator in the unconstrained optimization function we convert that into a smoother function. So this was our objective. That's all. Thank you.